Questions about anything from last time? Yeah.
This isn't the last time. On the homework on page 141, problem 17. Can you clarify what that question is asking?
41. 17. Yeah, so in page 141, number 17, they're saying they have this function f from 0, 1 into the real numbers. It takes only, let's do the case rational numbers. Takes only rational values. Meaning that f of x is rational, so it would be in Q for every x. That's what that means. And then the question is, let's see. Oh, it says it's continuous. I would ask, could f be continuous? That would be another similar question. And if it was continuous, what could you say about it? So also, f is continuous. What does it say? Well, they tell you the answer, f must be constant. So that's what you're supposed to show. What tools come to mind when you think about that problem? Yeah. Intermediate value theorem is a big one. So let's say f took two different rational values, then it would have to assume every value between those rational numbers. And what happens in there? Yeah, that's the density. So the big hint, there are two big facts. Hint, intermediate value theorem, and the density. Actually, in this case, it would be the density of irrational. Let's see, the irrational ones are I minus Q in I, the interval. That'd be big enough. Yeah, that's, and then they ask the same thing if it has only irrational numbers, and we know about density of them too, so it would be analogous. Other questions about anything? Well, we're on 6.1 now, and that's differentiation, and it's going to feel a lot like freshman calculus. And many of the proofs you saw in freshman calculus are 100% legitimate. But a couple of them were in order to get moving quickly, a couple of those famous proofs were a little bit sloppy. And so I thought I'd do the ones that are important that we can understand at a deeper level now, rather than all of them. So it's important to read 6.1 carefully. So read all of 6.1 carefully. Some of it will sail right by. Things like the derivative of a sum is the sum of the derivatives. That's a snap. But of course, we know the definition of, let's suppose f is defined on an interval and we take a c in AB. Then f has a derivative at c, let's say, if the limit as x tends to c of f of x minus f of c over x minus c exists and is equal to L. So it has to exist and is equal to some limit L. Then we say that f is differentiable at c and its derivative is L. F is differentiable at c, and we write f prime of c equals L. Okay. And I like to call that thing right there a difference quotient, dq. I don't have to write it so much. And of course, it's the slope of a secant on the graph. And as the x slides into c, the slope of that secant is tending to something. And that's the instantaneous velocity is what we think of derivatives as meaning. So you heard that whole thing when you were in freshman calculus, sort of from an intuitive point of view. So let's see, the first thing to show is that if f is differentiable at c, then f has to be continuous at c. So f differentiable at c implies f is continuous at c. That turns out to be an easy thing. Might have gotten glossed over in a freshman class, but the y is pretty easy. Let's say we have the difference quotient, f of x minus f of c over x minus c is tending to L. Some limit. Then that difference would be, I'll call this E of z for error. So this is the definition of E of z. I'm sorry, E of x. When I teach complex analysis, it's E of z, not E of x. That's the definition of E of x, and think of it as the error. That difference quotient is close to L, and that would be the error at x. Okay, so if f is differentiable at c, the definition of that derivative means that E of x goes to 0. So we know that if f prime of c exists, that means that E of x goes to 0 as x goes to c. Remember, in the definition of limit, it was important to take x unequal to c. The function we were taking limits of didn't have to exist at c. And that's we did that because of this day coming when we would have this difference quotient that clearly doesn't make any sense at x equals c because you're dividing by 0. Okay? That's why we did that back then. Okay, so E of x goes to 0 as x goes to c. Let's define E of c equals 0. Okay, that definition of E of x didn't make sense when x is equal to c. So I should say definition of e to the x, that's when x is unequal to c. Otherwise, that formula doesn't make any sense. But now I'm going to define e of c to be 0 because it's the natural choice. If I do that, then e of x is continuous. At c. Okay, and now take that formula up there and solve for f of x. I should call this something. Call this star. Solve star for f of x. It's a snap, and you get a famous looking thing here. This looks like a Taylor series. F of c plus f prime of c times x minus c f prime of c isn't defined yet, plus L times f x minus c. And that's equal to, let's see, that's f of c plus e of x times x minus c. Kind of ashamed to have a page break here. Let me copy this and paste it over here. Now think about what happens as x tends to c. We know rules of limits now. This is a constant, so of course this tends to f of c. One is a constant, so it tends to that, to L. This one, x minus c, is x tends to c, tends to 0. So we're using limit. The product of a limit is the what am I saying? The limit of a product is the product of the limits, etc. And then finally, the one that's interesting here is I have this e of x tends to 0. And of course, x minus c also tends to 0. And so we see that f of x, these arrows are as x tends to c, using the rules of limits that we've learned or proved. And that shows that f of x goes to f of c as x tends to c. And now I can write that formula. That means that L is the derivative. We're assuming that that exists. So back there I should have written, here's a nice formula to keep in mind. F of x looks like a first order approximation in the Taylor series plus the remainder term, e of x times x minus c, where everything in that equation is continuous at c. Where e of x is continuous at x equals c, if we write e of c equals 0. And that thing is like the remainder in Taylor's formula. And that just says that the remainder goes to 0 really fast. So you think of this as a r of x. The remainder, r of x, goes to 0 fast as x tends to c, because it's the product of two things that goes to 0. So it goes to 0 extra fast. Since both e of x and the other term, x minus c, tend to 0 as x tends to c. Okay, so that's an important fact to know. And then I thought I'd prove my favorite things for my personal. I used to have a little notebook where I'd write out these proofs just so they would stick when I was in freshman calculus. My favorite facts in my little notebook. Let's see, one of my favorite facts is that f of g prime is f prime g plus fg prime. And to demonstrate that, I'd have to take a difference quotient. Let's see, the product would be f of x times g of x minus the value at c, f of c times g of c, over x minus c. And you stare at that for a little while and realize, how am I going to relate that mess to difference quotients involving f's and g's? And eventually it would hit you to add and subtract something in the middle there. So let's see. What I want to do is pull that apart and sort of factor things out. And let's see, if I wanted to pull out an f of x, I would put here an f of x, but then I can put a different g, something that doesn't change, a g of c. Then I could factor out that would allow me to factor out the f of x term. And if I'm going to subtract that, then I have to add it back. And the amazing thing is that solves my problems for the first term, but by luck, it also solves my problem for the second term. Let's see. So a miracle kind of happens here. When I pull that apart, the great thing now is suddenly I can pull out the f of x term. And then what I get here is the difference quotient for the g derivative. That's too good to be true almost. But then the rest of it, a miracle happens. And now I can pull out the g of c term. And what's left is a difference quotient for f. So that's all there is to that trick. And now we know facts about limits. It's the limit of a product business again. And the previous thing I just showed you that f is continuous if it's differentiable. So this is important here. We're using the fact that f prime exists. So f of x goes to f of c. It's continuous. That's a very important thing right there. And of course, we're assuming that g is differentiable, and so this is going to go to g prime of c. This thing is a constant, so it just sits there. And this thing tends to, this difference quotient tends to f prime of c. So check. So the thing we didn't dwell on in freshman calculus maybe is the importance of knowing that if f prime exists, then f is continuous at c. So that's all there is to that. Question? No, the limit. F of x goes to f of c. Right, because it's continuous, being differentiable. Yeah, I'm letting x tend to c now in all of this. Okay, that's one of my favorite things. By the way, then you can show that polynomials are differentiable. So remark, x is the easiest function. I guess a constant function is easy to check that its derivative is 0. But f of x equals x. Then the difference quotient is x minus c over x minus c, which is 1. And of course, that tends to 1, equal to 1. So it's the easiest example of a differentiable function, and its derivative is 1. And so therefore, using the product rule, x times x is differentiable, which is x squared. So that's x squared. And so x times x squared is differentiable. Dot, dot, dot. And so all powers of x are differentiable. And then if you know, you can add things up and multiply by constants and maintain differentiability. So you quickly get that polynomials are differentiable. And you get the formulas that are famous for the derivatives. Let's see, polynomials are differentiable. And the famous formula d by dx of x to the n equals n times x to the n minus 1, etc. So that all follows from the product rule. And then my other favorite formula is that f over g prime is f prime times g minus g prime times f over g squared, where g is non-vanishing. Let's see, I used to think this was kind of fun to do. I want to make this as easy as possible. So I'm going to reduce it to the product rule. Let's check that. Let's check. The derivative of 1 over g is going to be minus g prime over g of g squared, where g is non-vanishing. That's the easy thing to check. Let's take the difference quotient. That would be 1 over g of x. We've sort of done this multiple times lately. After you do it multiple times, it starts to get easy. You do that, you do a cross multiplication on the top. You get, what do you get? I'll put the minus sign in front because it'll make it look nicer. I get g of x minus g of c over g of x times g of c, divided by x minus c. Then you see the difference quotient for g just popping right out at you. Minus difference quotient for g times 1 over g of x times g of c. Well, in freshman calculus, this is where you said, aha, this is obvious now. But something we dwelled on in the past is we need to know that if g of c is not 0, then there's a neighborhood where g is bounded away from 0. So in freshman calculus, you kind of slid this under the rug. We need to know, we know g of c is unequal to 0. And we need to know that g is continuous. It is because it's differentiable. Implies that there's a little neighborhood about c where g stays away from 0. So that thing in the denominator doesn't kill us. So g is continuous at c. Yeah. And we know from recent experience that that implies there is a delta. Let's see, let's call it like a min, an m bigger than 0, such that G and a delta, so there's an m bigger than 0 and a delta bigger than 0 such that G of x is greater than that m when x minus c is less than delta. And now I can, do I need that? Actually, we had some corollaries of that fact back when we needed it. We do need to know that, but we can use the facts about differentiation. I mean, facts about products of limits. See that thing up there? Let me copy it. That's interesting. Look at that. Next page. What? That was stupid. Huh? I'm sorry about this. Okay. I guess the thing that's, we know that this tends to minus g prime of c. And we know that 1 over g of x, since g of c is not equal to 0, tends to 1 over g of c. Okay, and that thing I said we needed it when we showed that if something is in the denominator and tends to a non-zero value, the limit of the inverse is the inverse of the limit. Anyway, that's not a big deal. Okay, all the rest of them, yeah, so next, once you know that, you would use the product rule. F over g would be f times 1 over g, and you use the product rule. So this is f over g prime. That would be f prime times 1 over g plus f times the derivative of 1 over g. That's minus g prime over g squared. And then you play around with algebra and you get the famous quotient formula. Okay, so those are done. Now the biggest thing you saw in freshman calculus that was sloppy is the chain rule. And so I'm going to take f of g of x, let's say f composed with g prime. Let's see, let's let h of x is equal to f of g of x. Then the famous chain rule formula is that h prime of x equals f prime of g of x times g prime of x. So in this, if I were going to write out all the hypotheses, I'd have to have intervals where f and g are defined. G would have to map to where f is defined. Those derivatives would have to exist. I'll skip that and let you read it in the book. But let's see, so the freshman calculus proof of this is sloppy usually because you just want to get done with it and move on. Oh, what do? They look at the difference quotient, f of g of x minus f of g of c over x minus c. And then they do this to get moving real fast. They have f of g of x minus f of g of c they put the x minus c over here, and then they multiply and divide by the same thing, so they don't change that quotient. And the thing they do is g of x minus g of c. And then you see, oh yeah, that's going to make good sense, because if I let y be equal to g of x, then that would be an f of y minus f of g of c over y minus g of c. That would look like a difference quotient right there. And if they did say that differentiable functions are continuous, we would know that g of x tends to g of c. So that's going to look like a difference quotient, f of y minus f of capital C over y minus capital C, where y is equal to g of x and capital C is equal to g of little c. Okay, so the y would tend to the c, capital C, as x tends to c. And that would make the chain rule pop right out. But what if I could be dividing by 0 there? And that's the thing that's delicate and you have to think about. So I could turn this into a real proof. But I'd have to split it into cases where the derivative of g was 0 and where it wasn't 0. And if the derivative of g wasn't 0, I'd have to show this thing in the denominator wasn't 0. So this convinces freshmen real quick that this is a true fact, because it looks so simple and natural. But the head scratcher, and sometimes there's a nasty, smart little freshman in the audience who calls you to task on this and slows you down a bit, and you have to admit to being sloppy. What if that stuff in the denominator, g of x minus g of c, equals 0 for x close to c? Now that we've seen more functions, we know that the sine 1 over x thing, it's like, think of a function that does that. X squared times sine 1 over x. That goes to 0 pretty fast. Has a whole bunch of zeros as x tends to 0. And so if you start thinking, oh my gosh, what would happen in that case, you realize this proof is going to bomb. If the derivative is not 0, the g derivative, then you can salvage that argument. But you have to think about it and do some work. Anyway, this proof I'm going to show you is the easiest and correct. So that's my goal here, is to do an easy and correct proof. Okay, so I know that f of y is differentiable at y equals g of c. And so that thing I did earlier, I wrote that f of y is equal to f of g of c plus f prime of g of c times y minus c plus an error function, e of y, times y minus c. All I did was change the x's to y's and the c to g of c in that formula. where e of y goes to 0 as y tends to g of c. And you remember we let e of g of c be 0 to make it continuous. Okay, maybe I should put that in a big red box. Call it star. Okay, let's mess around with star a little bit. Now, let y equals g of x in star and pull it apart a little bit and mess around. Let's see, so there's star. I'll have f of g of x. I'll pull see the f of g of c on the right? I'm going to pull it over to the left. Okay. That's equal to f prime of g of c times g of x. Oops. Oh, doggone it. I'm sorry. My c is actually a g of c. There, that's fixed. Now I'd have g of x is y, and I'd still have a g of c here. And I have an e of g of x times g of x minus g of c. Okay, so all I did was rewrite star and pull that one term to the left and replace the y by a g of x. Then when you stare at that for a second, you realize, aha, that's my difference quotient. So if I divide this by x minus c, that's my difference quotient with a composition. And then you realize, okay, when I distribute that x minus 3c through, here's the place I should stick it over here. And here's the place I should stick it over here. And as I let x tends to c, well, this is a constant. So this is as x tends to c. Constant just sits there. This tends to the derivative of g. This one's easy. This one tends to the derivative of g. But now this is the one we need to be a little bit more advanced to think about. I claim that this one is the important one. This one's going to tend to 0. And we have to think about that important red one because we're using the fact that, what do we need? We need e of g of z, e of g of c equals 0. And we need to know that e is continuous at g of c. So I defined it to be that. That makes it continuous at g of c. And we need to know that g of x tends to g of c. So that we know that composition of continuous functions are continuous. We probably glossed over that in freshman calculus. That's a check because G prime exists implies G is continuous. Okay, so that's the adult proof of the chain rule that doesn't do anything sloppy. Questions about that? Okay. Then when you're talking about the basics of differentiation, there's one more biggie to talk about, and that's the inverse function theorem. And you might remember at the end of last hour, I talked about a continuous version of the inverse function theorem. This is the differentiable version. So that's what we're going to talk about now. But remember what the continuous version was. F, continuous and strictly monotone. On AB then the inverse exists and is also continuous and strictly, then F inverse exists and is also continuous and strictly monotone. Of course, you're mapping intervals to intervals because that's the interval theorem. So strictly monotone. We did that last time. And the picture was, I won't draw the picture again. I added some pictures at the end of the last lecture. So if you consult the notes, you'll see some things I didn't say last time. Okay, so the differentiable version is going to add keep the hypothesis of the continuous version and add f prime of c is unequal to 0. Okay, so let me draw a picture. Let's do the since I'm running out of time, let's do the increasing case. Okay, so the increasing case, I'd have, you make it kind of look like an S if you like. Here's an A, here's a B, goes from A up to capital B, and this is a graph of f of x. It's supposed to be strictly increasing, so I better make it a little bit steeper. Still, I want it steeper. That derivative isn't 0 at the top. Can't seem to make it not look 0. So that's a graph of y equals f of x. Last time I showed you that the inverse function you'd get by flipping that about a line y equals x. Then you get the graph of y equals the inverse, x equals the inverse of f. Okay, and here we have a point C somewhere in the middle, and we'll have did I say? Yeah, f prime of c needs to be unequal to 0. In the increasing case, f prime of z will be strictly positive. F prime of c would be strictly positive. And then the fact is f inverse function prime, let's see, at f of c would be equal to 1 over f prime of c. That's the inverse function theorem, and that's the famous formula that falls out from it. What's another way to write the same thing? F inverse, I don't want to do that. That's the formula. The hard part of the inverse function theorem is showing that the inverse is continuous. But we showed that. The hard part of the inverse function theorem is showing that the inverse is continuous. We did that last time. So that's the hard part. It's done. I claim that after you know that the inverse is continuous, then this thing is a snap. Let's let g of y represent the inverse. And we think y equals f of x. Okay, I want to use a difference quotient to calculate that derivative. The difference quotient would be g of y minus g of f of c over y minus f of c. And here's the sneaky thing to do. That's 1 over y minus f of c over g of y minus g of f of c and now I'm going to let the y be f of x. So that would be y is f of x minus f of c over g of y is x. G of f of c is c. Okay? And what I know now is that g is continuous. So the important fact, g is continuous, and f of x tends to f of c as x tends to c. And so g of f of x